Heavy industry operates on a scale that demands a continuous supply of energy. A turbine generator like this one pushes out thousands of megawatts to keep factories and municipal infrastructure running without interruption. But trace the electrical grid back to a standard household, and the energy footprint drops. The power demands here are simple, intermittent, and low voltage. The separation between these two environments reflects a physical divide. While the home connects to a single phase of electricity, the factory requires three. The reason for this dual system comes down to a unique physical limitation built into the nature of alternating current itself. This chart shows a standard single-phase alternating current. Because it travels as a wave, the total power mathematically drops and hits exactly zero every time it crosses the center axis. For basic loads that rely on electrical resistance to create heat, this momentary drop in energy is invisible. A toaster stays hot even if the power technically pulses on and off 100 times a second, but applying that same pulsating power to heavy rotating machinery is a mechanical challenge. It forces the physical driving power of a massive motor to drop to nothing 100 times every single second. This electrical pulse creates severe mechanical consequences. The motor experiences uneven torque, leading to vibration and metal fatigue in the shaft and bearings. You cannot build a heavy industrial economy on a system that constantly turns itself off. Engineers needed a mathematical workaround to eliminate the pulse. This graph represents the solution. Instead of sending one wave of power down the line, the grid generates and layers three separate alternating currents onto the same system. The trick is spacing these three waves exactly 1/3 of a cycle, or 120 degrees, apart from each other. Watch the vertical indicator sweep across the timeline. Because of this offset, whenever any single phase drops to zero power, the other two phases are active, delivering energy into the circuit. When these three overlapping pulses are added together, they mathematically combine to deliver a flat, uninterrupted flow of total power to a machine. This 120-degree offset eliminates the mechanical thump. It allows a motor of any size to generate smooth, continuous rotational torque. To physically generate this offset, power plants arrange three distinct sets of coils equally spaced around a single spinning magnetic rotor. You might expect a system with three independent circuits to require 6 massive cables, but by arranging the generator windings into specific Y or delta configurations, the three phases share their return paths. Looking at the single-phase equivalent math on the right, the voltage is divided by the square root esprit. This shared wiring geometry allows the grid to deliver higher line-to-line industrial voltages using smaller cables. By utilizing shared conductors to carry three overlapping phases, the grid achieves massive distribution density. This ability to deliver significantly more energy with far less copper is what makes the construction of the modern high-voltage grid economically viable. That transmission efficiency is crucial, but the physical advantage of three-phase power is most obvious once it arrives on a heavy factory floor. When you connect a motor to a three-phase supply, those electrically staggered currents automatically translate into sequentially staggered magnetic forces inside the motor housing. Because the coils are spaced around the housing, that 120-degree electrical delay naturally generates a magnetic field that physically rotates in a circle. This continuously rotating magnetic field reaches in and drags the central metallic rotor along with it, creating instant motion. Single-phase motors struggle to start spinning on their own, often requiring extra starting capacitors. Industrial three-phase motors, by contrast, are inherently balanced, self-starting, and mechanically superior. Despite these mechanical and economic advantages in heavy industry, three-phase power is not intended to replace single-phase power entirely. Single-phase is optimized for residential neighborhoods. In these environments, loads are light, and keeping the wiring simple is the highest priority. Three-phase power is reserved for mission-critical facilities, factories, and tech infrastructure, places where operations require high power density without any mechanical interruption. The two systems exist in symbiosis. A standard home only requires the simple supply of a single phase, while a massive data center demands a constant, high-density stream of energy. The modern grid is a marriage of these two distinct physical realities, working where they are most effective. Electricity is generated as three-phase power, transmitted across high-voltage lines, and separated into single phases right before it hits a neighborhood wall outlet. The heavy infrastructure of the modern world does not run on brute force. It runs on the precise mathematical timing of a 120-degree offset. A single-phase circuit provides the light we need for a living room, but the constant, balanced force of three-phase power is what drives the heavy industrial engines that power our society.